any question or problem with the slide? No? Okay, yeah. I think there's one problem that I have to interpret the output from lesson regression. So the only thing I can say to you is to refer back to our PowerPoint slide or other instructional data extension. But there's one thing there. Just don't feel confused about the graph, right? So we usually have something like, so here's zero reference line, right? So and here's the lambda, and here's the vertical axis is the magnitude of your beta coefficient. So you have a couple of showing the effect of some variables here. X1, X2, 3, S4. Showing the effect, estimated effect of this this coefficient as a function of the penalty term. Right. So in some of the output, you might actually read that, oh, this effect is extremely large, all the way to say negative 200 or even like 120, something like this. So, but the final output, when I read it, so I specified in the investing net package, they use S in lieu of lambda, I think, or alpha. So it will show you the output, evaluated, estimated at the optimized lambda. So I said, well, the range of the effect looks okay, but it's not how I saw here. Yeah, that makes sense because it shows the range of the estimated coefficient for those right-hand side variable as a function of lambda, the penalty parameter. So there could be a number of lambda, but the output that you get are estimated as optimized data. Okay. So that's why you always see, okay, so if you create the output since that they are distributed within the estimable range, that looks fine. Let's compare the here. So you can see that almost like unregulated. That's perfectly normal. It only shows you how does the effect vary as a function of penalty term. And as we know it, the greater amount of penalty, right, the greater the size of the penalty, the faster they have observed that, the more accelerated the penalty process, which means that more variable will be kicked out from the regression, meaning that they fail to get the sizable beta, sizable coefficient, meaning that it probably doesn't have really significant effect on the dependent variable, right? Right? Okay. Yeah, so that's it. So don't feel strange. It'll be show you how that varies as a function of data. And for those of you who haven't sent me your term paper proposal, you should be quick. I mean, it doesn't need to be very long, but simply just tell me what you want to study, and if you have the data already, and what your proposed model to use. Okay. So this topic is much like a very light topic. It's very simple. So there's only two parts. So the first part is unsupervised study. So since we haven't talked about, we're already talking about a couple related methods under the domain of supervised learning, meaning that the outcome variable are labeled. They're clearly labeled, or actually say at this, if you assign it a label. Right? But most of the time, they're labeled unsupervised, meaning that they do not have a clearly distinguishable label. Of course, I mean, in human interaction, that like we don't want to be labeled by someone. You have a kind of person. No, of course, that's the stereotypical thing that's not undecidable, but But sometimes for regular label, we want those label observation to be labeled. So if we look at the process or for ease of computation. But we're also talking about pre-processing. But finally, we get down to the topic that we have been using all along. Classification, classified performance, or classification performance. I mean, they have been using in previous assignments have asked you to compute the accuracy score. So you might say what that means. But today I'm going to tell you what they really are. So talking about story, my story, a story from my younger sister. A couple of years ago, when she first came on stage, so she worked for a Startup company. So they invest in food delivery services, but of course it's not Uber or the food panda. Because at that time, the food delivery services like just flooding everywhere. There are things that more than 10 to 15 of them today. So they are competing to enter into the Taiwanese market. So they sent out their headquarters not far away from here, that local headquarters. So they actually work on a third-party software code. I just go back in this like essentially just a heat map mapping the density or the intensity of your business and or your business number. So that can be converted into the process of data so that you can do some analysis of it. So they found out, well, it seems that our business is booming. But it's strange because if you map out the data's geolocation, find out that most of the ticket or simply most of the business comes from, say, not too far away from our capital, from our Taipei capital. And this is the problem, right? That percent of profit. So they actually find out that actually a lot of their coworkers use the subsidized rate to hold it for themselves. So that's where most of the business. So so you know, in 6 months of time, they close out this business. Right. So you might wonder, like, so what do data point also to get a reason like this is see that okay, so each data point represents a ticket or something like that represent an order, an online order. So what does data point cluster around our particular location, for example, like our headquarters? So here is a concept of clustering. So clustering is an unsupervised learning technique, meaning that the outcome is unlabeled. So we use this label to group together a set of data points. That in a way that under the assumption that the data point within a cluster are more similar to each other than outside of it, than data point outside of it. For example, if I do some the student major in political science together, and I create another cluster because the student econ department or other department. So you might say, okay, so which means that the student that under the cluster of political science, they probably share some kind of affinity, per se. They are similar in some way. The most obvious attribute would be your college major, right? Or you can say, oh, it seems that most science majors are female, but econ they are male. Well, it's not generalities. What's actually true? And so it's fair to say that similarity in itself is actually is a quantity, or simply quantifiable information that reflects strengths of association, or the strengths of relationship between any data point. Right. So based on some scientists, or we can say, if there are two data points that are closer together, then they probably share stronger relationship than data point outside of it. And then for the researcher or data analyst, they definitely want to study. So what variable make them closer together as opposed to materially apart. So cluster is mainly used for exposure data science when the dependent variable we analyze means that the variable and we want to label, we want to create a label, they do not have a clearly distinguishable label. So we have to say, oh, hey, cluster together means that we do not have a clear, probably do not have a clear concept as to which subgroup they are and how to differentiate them. We can say, okay, this is a layer cluster together, but we do not have it. At the present moment, we cannot assign it clearly. When you say, oh, they're clustered together. So there are different types of clusters. First, a hard cluster. And so each data point belongs either to male or female, for instance, gender, either to this cluster or the other. It must be one or the other. So you can say gender. But then, of course, since we are living in kind of great diversity, I think that most surveys will say, identify your gender at the moment. Because actually in some countries, because nowadays they actually allow people to choose their gender, to change the gender at different time. Or you can easily modify your gender identification. You can say, oh, I'm a male at this moment, and probably like 2 minutes from now, you can say, oh, I'm going to prefer to identify myself as a female. Or you can say sub-cluster. That's a topic that we are going to run into 2 weeks from now. You say, the data point may actually belong to multiple clusters. For the text mining and analyzing a document, because in a given news article, the same amount of text may actually refer to multiple concepts. For example, if you want to, for example, the title of the document, you say the economic impact of the Russian-Ukrainian war. Well, so the news article actually referred to a couple of things. Talk about the current news, right? This news article, or the war, the ongoing war between Russia and Ukraine, or its economic impact. So it may be related with financial news, or maybe the focus of that news is your financial news. You just tap on the ongoing Russia-Ukrainian war. So we don't know exactly. So you could treat that news article as a single document, or simply as a single data point in collection of news article document that you collected to do text mining on. And then that data point may actually belong to multiple clusters or a topic. So the first method we're going to talk about is the k-mean cluster. It means that clusters are represented by a central vector, or in spiral diagram they call it centroid. However, the centroid may not necessarily be the member of the cluster it was originally assigned to. And another related concept for hierarchical cluster, meaning that data points that are closer to each other are more similar, of course. And data point and this cluster, so it kind of they're formed by connecting data points according to their distance. So that for similar data point, if they belong to the same cluster, mean that they probably be separated by shorter distance. Or the similar data point, they have longer distance from each other. So let's first begin with k-means. So k-means, you say, is that similar to the k-nearest neighbor we talked about last week? Yes. Because the k's just means the originally assigned cluster central, meaning that most data points are clustered around the 3 central vector or centroid that we assign. And this could be true or not so true because it was actually assumed, right? So given the data, you can say, well, let's say, some people might help you say, oh, that's disputable, meaning that he or she might not agree with your cluster assignment. So you might actually heard that person said, it looks to me there's a 4 cluster, but there were 3. So there could be some disagreement between your assignment and his or her assignment. But anyway, the algorithm, workforce algorithm, we call it particle 1 algorithm. So we actually define using the metric that you should be familiar right now. You seek to minimize the within cluster variation as the sum square Euclidean distance between any 2 points. So here, so after we assign cluster centroid in the data point. So the algorithm will compute the Euclidean distance on a two-dimensional plane, x, y, between 1 point and the assigned centroid. So if we group a set of data point that minimize the sum square Euclidean distance, then it should be assigned to the cluster. So the mu is just the mean value of the cluster. So that if the algorithm minimizes group of points surrounding the cluster centroid, then they assign it as a cluster. So each data point is assigned to any of the k cluster that we assume, we say k equals 3 or 4, such as the sum square Euclidean distance between a given data point and the assumed centroid is minimized, so that cluster is created. So how it works, of course, you begin by first randomly pick k point out of all the data points. So you can say the first stage is actually pretty good. So we say, so we simply randomly pick 3 points as the cluster centroid. And then we compute the distance. Right? So we are left with n minus k, so those data points, and then we assign 3 randomly assigned. It's not, we did not do this on purpose. It's randomly assigned because we are going to update the information. Right? So after the first assignment, this gives us with n minus k data point, which are left to be determined for its cluster groups. Okay? And then we use the particle 1 algorithm to compute the Euclidean distance, sum square Euclidean distance on the coordinate. So with the data point, this data point is definitely closer to this centroid. Right? So we just assume that 1. So it will be true. This, it appears that closer to this one, okay, rather than this one. But this is disputable. So I just tentatively also place on this respect. And so on and so forth. So the algorithm, so after the first assignment, so we use the figure in the first assignment. The algorithm will then compute again the new mean value for each cluster. For example, it might actually say the algorithm will check the sum square Euclidean distance of each data point to see actually some of the data point may actually be closer to a different cluster. For example, like this one. But depending on how you look at it or your angle, because the algorithm might actually find that, it's actually closer to cluster 2 instead of cluster 1, and you will update this information in this cluster, but it's called centroid update. So after all the data points are reassign a kid, you will then check the kid to reiterate this process, and then create a new updated cluster name. We're going to talk about different kinds of clusters. It's called hierarchical cluster. So you see that over here, it seems that we're just doing this on the all the thing, right? It's not hierarchical, simply it's not layered. Or it does not have level. But the hierarchical cluster isn't, it does have level. So it's an algorithm, it's a classification algorithm that groups similar objects into a group, also called cluster. But the method of doing that is quite different. Because at the very beginning, suppose you are given your data set, your data in data point. This method essentially treats each data point as a cluster of its own. So when we use the word cluster, it means that it probably contains multiple data points, multiple observations. But in hierarchical clustering, at the first stage, very beginning, each data point is itself a cluster. So simply, if you get by treating each observation as a separate cluster, as a cluster of its own, and then it repeatedly do the two following steps. It first identify the two clusters closer together. So based on the X variable, the attribute that we supply, or simply the algorithm will do that simply by computing their distance. You see, so the algorithm might say, okay, so it looks like this 2 point are closer. So I will group it into one. And then we find out, oh, since that this one, which is the merge data, this 2 point, is closer to this one. Right? So I would then merge, create another data point. So you will begin by first merging the two most similar clusters, or you can say most similar data point, because at the very beginning, the first stage, each cluster refers to a single data point. So you will continue to merge again until all the cluster, or say a total data point, are merged into a single cluster. So you can see it continue to grow, unlike our tree-based model that I introduced last week. It goes top down, but here it says bottom up. You will continue to merge again with other data points. This data point, and then this data point, until all the data points merge into a single cluster, which covers all the data. Okay, we simply borrow, the mechanism is actually borrowed from what nowadays people like to call network science. Meaning that, so the topology of your data, probably should use that topology. Now, the structure of data consists of multiple nodes, or you like to call it multiple nodes, and ages. Ages is the line that connecting any two points. Network science, the entire universe consists of nodes, right? And the line that connecting anything else is called the ages. People in the network science, so the network science work also use similar technique in terms of whether two now closer to each other, whether they should be grouped into a subnet. So you measure the period-wide descent variable between any data point. Because also, again, if are happening on our side, because, for example, like sociologists, they have to talk about the similarity, because people who are more similar tend to group together, right? So if you actually plot out their relationship, you'll find out, oh, we go all similar hue, or there's a same person with better fall together. Right? If you're a similar hue, actually, we are mingle around each other, mixed with each other. Or people who are more dissimilar, they are followed apart. So there are several related concepts. First, single linkage. You measure the closest pair of points. So for here, the closest pair of points, like this means that we minimize such distance. Or there are complete linkage. That means how long does it take from one point to the farthest, to the point that farthest away. And their distance determines the complete distance of the entire network. Or simply you can say the entire data set, because the network consists of all the data. The average data point. The average data point is the measure of the average dissimilarity over all pairs. So you can say this point to this point is total distance is 1. And this point to this point is 1.5. And this point is 2. And we take average of this pairwise distance. And to calculate the average dissimilarity. Because dissimilarity is increasing in the distance between two data points. So you can say it's simply a function of the distance between data points. So the data point that follow apart, they are more similar. The data point they are more close, they're more closer, they're much closer, and they are more similar. That's how we interpret it. And at group level, or at cluster level, there's a concept called centroid linkage. You measure the dissimilarity between two clusters. It's simply just the distance between their cluster centroid, their group centroid. And in practice, centroid linkage can determine the extent to which you are willing to trade the differences or dissimilarity between two clusters and treat them as well. So now we jump to some exercise. So again, we have this K-mean cluster and this hierarchical cluster. There's some unlabeled data, and some of them are actually harder to understand. It's not the kind of social science data that is familiar with. So as usual, we first install all the required package. So we need this HB classify and line data, which we're going to use for today. So this variable are really important to understand. So I actually represent it online to find out their original name, and then I rename each of the columns listed up. Just that they're chemical compounds, right? So it's really hard to understand how we can actually leverage this column as variable to predict, to classify this different type of water. Or I mean, that is from layman, like you and me, but you said, no, I'm actually a one answer, so you probably know how this is. So we first rename the column, the renaming actually is very important. So you should first check out what's the dimension of the data, right? So we have 13 column means that 13 variable, 13 plus 1, because we have those are cluster these observations. So that for renaming, we should show you the column, number of columns that need to be renamed. So you will generate a vector that include the name, the number of here I use test string, number of new names corresponding to the column lengths of the data frame. So if you want to read any data, you need to pay attention to that. Then we simply set a random seed. And directly go straight to the action. Just you apply k-means function. Specify our data set and set k to 3 because initially we want 3 clusters. And then we need to invoke useful package. Package name useful for obvious reasons. And plotting is just simple. We just include our clustering, k-mean clustering output as our first argument, and specify the original source of the data, original data source, and it will generate that for you. You also include a title. See that? Okay, so but say, how do I know this clustering result is any validity? How do they correspond to the actual type? So to do that, you can, there are a couple of ways to do that. We can evolve abstract. It's very useful because it can actually come in handy to help you plot out the contour of the original classification. You can see that there is, so we're discussing the code. So you simply apply VIZ, visualization cluster, and put your k-mean cluster output as the first argument, and as a specified data essentially is set as in previously used. And then you will generate a contour plot showing that how good your classification correspond to the original type. So see that your classification result, the k-mean cluster result, kind of good at mapping out the original classification at the boundary, but probably not so good in the middle. Right? So there is still some data point that should supposedly belong to different type of form, but was being covered by our k-mean clustering result. You can also map the original one type by different kind of sequel, but it's not as clear as the previous one. You see that? Okay, so there's something wrong here. Especially regarding the third type. Okay, so there was something that could go. So for the cluster 3, actually can intermingle with the second and the third type. For the two others, clustering result, I believe were quite good, especially for the first time. Right? But they're marked by the original type marked by a circle. We call it in red. It's not bad. But the k-mean clustering is, as I said, the first stage is random. So it's very sensitive to some random perturbation over some stunning condition. So because one way to mitigate against it is, of course, to do multiple runs. So we have said another, we haven't used this traditional one step. So we can actually do the random run like 25 times. So that's how we do it. So again, you need to set random seed. And different random seed will generate different outcome, different randomized program. So we said, let's start with 25. You can say that you can set to different numbers, 200 or 150. And then we can compare the clustering result of the original one and the one when I said let's start with 25 and 25. I just simply name the k-mean clustering of the one, k3 and 25, and then do anything you want. So we compare to that. It seems that the classification outcome is more balanced. So here it comes to a draw. It means that we need to do some birding on the clustering outcome. So how good is the clustering? So there's a usual rule of thumb is that if you have a value that's greater than 10, that means okay, it's fine to continue to add additional clusters. So let me explain that again. So we need to determine the optimal number of clusters according to Hartigan and Longstreet. So this method, the recommended method is that you will compare the ratio of the within cluster sum square Euclidean distance that's calculated at k equals say 3. Calculate at k. And as I showed you previously, that means we need to randomly assign k point among the data set as the centroid. And then we group the n minus k data point according to their sum square Euclidean distance to those centroid. And then we will check that again to see that pretty much closer to a different cluster. And then finally, when we group this data into k cluster. And this will give us statistic, which is the within cluster sum square Euclidean distance. But you might wonder that for k plus 1 be a better clustering number, right? Because as we look further up here, it seems that our the k equals 3 clustering result isn't quite good at clustering those data points, especially bad at distinguishing data point for the second and third time. So should I create add additional cluster to tackle those misclassified data point, maybe -1, simply grouping into 2 clusters. So here's the group. We said if a Hartigan score, which is just a ratio of the within cluster sum square distance. So that is under k central. So that's the definition for Hartigan score. So the general rule of thumb is that if it's greater than 10, then that means that, okay, so there is an extra error here. The error is quite noticeable, so we should continue to add 1 additional cluster. So we have to plot this out. So we do the same code, we also need to see. So another good thing about this code is that if you do not want to try to economize on your say line of code, then you can directly set your random seed here. So we need to invoke this function called fit-names. So that will create an object, and we can plot it directly using the plot Hartigan here. So here's the result. So we should continue to add cluster all the way up to 16 cluster. Because beyond 16, and then the Hartigan score begins to drop, right? And so it also show you the legend here. Well, I didn't do anything here. It's just automatically creates that. Very easy to read, right? Okay, add cluster, yes, no. So that means you should stop here. but you can run extra risk. No, I'm good. I can have one extra at in T. Right? So but here's more like a confusion matrix way to compute your clustering result against the true type. So just create a table. Okay? So here's the true value. The one data is by data and subset by type. Type is on the column showing the type of this one. Against our clustering result. We need to subset the cluster label on the Kinney clustering output. Just create a table. So this will show up on the column, and this will be. See that? It's just that we don't run problem for the second type. It seems that we are pretty bad at distinguishing, say, the first type of one and so the third type one, but there's also, if you want to visualize the outcome, you can create a confusion matrix as a table. So here is percentage, but you only need to plot out this table and then you will show you the number of agreement between the true value and your clustering outcome. And measure by the area of those rectangles. Those are measured by this rectangle area. You see the proportion of their agreement. Since that they at least agree on the third type of one, which is indeed true, but it's 0. So now we get to hierarchical clustering. So here in the exercise, I ask you to map out the distance using a complete linkage. Right? I mean that to measure the distance between the most dissimilar data point and the data. Right? I'll go back and look at our slide. What's the definition for complete linkage? Measure the farthest pair of points, meaning that with this most dissimilar data point in the data. Right? But here, in this R exercise, I want you to calculate the complete linkage inside the data that given those. So here, you see, it's wrapped around the HC plot around your clustering. The function itself. You see that inside of this function, let's apply it to this. And you see one data, my first argument, and that's so what does it do? You return the distance measure. You will calculate distance between each data point. Calculate your method. As I said, the same method to Euclidean. Look at the Euclidean distance between any data point. Then inside of the HC cluster function, you calculate the complete linkage based on this pairwise Euclidean distance calculated using this. Because this function will return the distance station for each data. Pair of one. And then I use the hierarchical clustering to calculate the complete linkage. And you can map this out. So we will show how to cover that merge. So instead of my test being cut at the bottom, but you will show you this process. Most similar data are being grouped together and all the way up, all the way up is our person. And until even the most dissimilar data points can be one single cluster. And also compare the classification performance for different clustering that we classify from the hierarchical clustering works. They said, okay, I will come after I pay 3 costs. And we'll create using a tree function and create an object. And I can compare this classification result using the hierarchical cluster compared to the true type. It seems that the first one is way much better than when we use the KD. But it seems that the second one is not screw. So there's definitely some trade-off here. So I actually didn't spend that much effort here because it's only for pedagogical purposes. So if you want to say how to play around with the data using say more refined classification algorithm or something to include more parameter in your classification, then you can want to work on to do that. And here's the opportunity because previously we have worked around with the wine data, right? So there's another data called coffee data, so we can work around that to see and classify the type of coffee based on the origins or variety. Any question here? Right, so now we move to the Marriott topic about classification performance. All right, so whenever I went around, I talked a lot about this model and method, right? And you kind of complete this, the third one is still ongoing, with the 3 assignments, and probably have played around with your data account and also some of the data on your computer. Okay, so now I eventually can handle R. And also I have read all those material that they assigned to me. So how good is my model? It's the predicted performance of my model. Because if the main task of my analysis is to demonstrate this planetary power of my model, meaning that how much variance in outcome is explained by the model, then that can be easily done. So especially especially if my outcome variable, the dependent variable is a continuous variable, that's easy. I simply look at R squared. But R squared can be misleading, right? If you just want to inflate your R squared, then you can just use one to say lag value or lead value of your dependent variable. So lag value. Then without a doubt that you should definitely get a really high R squared, right? And there have been some controversy, especially when say social scientists try to get into the term of data scientists, or for especially they try to run a model that talking about the term of this prediction error, meaning that you're going to stock market, and they will find themselves really frustrated. So it seems that my model can predict, say, the rise and fall of the regime or some economic trend, and then they got really discombobulated. But so then this comes to a really philosophical debate about what social science really should be. And there are some social scientists that just want to take a step back and say, no, we don't do prediction. But I mean, you probably heard something about what happened to that? You say we don't do prediction. I mean, so that political scientists are knowledge to predict election outcome, right? That's all people care about. But there's also social scientists that say, oh no, our task is to explain how this already happened, right? So that you have those data, right? what already happened, so that you can fit the model on the data given to you. But it's not our job to do prediction. But however, there are other, from other disciplines saying that okay, the only hard task or the only objective task to evaluate your model is to see how your model performs in predicting some outcome, yes or no, and by what percentage do you get it right. For example, it's I fit a classifier model, usually a binary or polynomial classifier. So it could be a logit or SVN format machine or a gradient boost machine. So it's right 50% of the time, but around 50% of the time, and then people will tell you, it's not much better than if that was simply classified. Just a good job. We can say my classifier predicts 30% of the null as yes. And so how should I describe the accuracy of my model? And here is the main topic for the second part of this lecture. So we take chemistry after that. So you heard about this, what is type 1 error? So you say, after you made a statement, you say, reliable to type 1 or type 2 error. You know what it means. So type 1 error means that you incorrectly reject actually true null hypothesis, meaning that the actual event is false. Only can say something that is a negative outcome. Meaning that this thing does not exist. But your test result erroneously indicate that the actually false condition is present. So in prediction outcomes, this one that is the prediction outcome, meaning that we predict this to be true, while the outcome is the real outcome is false. That's what you said. Well, under current technology, that may cannot be corrected. That is just one thought. Correct me if I'm wrong. Maybe that in 10 years time, I think it will be wrong. But just for the sake of argument, just set it up here. But the diagnosis that the doctor predicts, you're correct. Meaning that, okay, so you predict the outcome to be 1, but well, the true condition is 0. Right, so that could be type 1 error, meaning that your model predicts a positive outcome, but it's false. Right, so that's very intuitive, right? So false positive. You predict it to be positive, but it's false. Because the actual outcome is a negative, meaning that is a true null hypothesis. But your model, or your statement, saying that the actually false condition, the actually false positive condition is present, while the true condition is negative. So that's called false positives, called type 1 error. On the other hand, during type 2 error, you fail to reject false null hypothesis, known as false negative, which in other words says your model predicts something to be negative, to be 0, right? While the actual event is what? So your predicted outcome is 0. The actual event is 1. Like this. The one is is obviously corrected, but everything like all the years plus, you'll say, no, this is just bad, and that's not true. It's completely correct, right? Well, the doctor predict that even now. So this occurs when you fail to reject a false null hypothesis. Meaning that the null hypothesis, we try to recall on the first couple of weeks, or lecture in the first couple of weeks. Null hypothesis means that this relation does not exist, meaning that they equal 0, right? Your model failed to reject false null hypothesis, meaning that the actual event is positive, meaning that something does exist. But you fail to reject false null hypothesis regarding the outcome that you're predicting as false or as negative or as null. It's 0, right? While the actual event is 1, it's positive, it exists. So your test result, you will need to reject the presets of the actual event in favor of a false negative, in favor of the negative outcome, but it's false, right? And also, one of the interesting things is that the chance of committing is 2 types of error, right? Actually, inversely proportional to each other. So if you type in a discrimination fashion for rejecting one type of error, and then the chances that you're committing another type of error will actually increase. Let me use one example to show you this. So this, people have said that, I would say, for a related concept that we're gonna run into in say 5 minutes. There's a matrix for evaluating application performance called receiver operating characteristic. The actually owes its origin to World War II, when actually there's a nation at war, and then some nation actually implemented blockade by placing sea mine along this key trade route. Because this container ship didn't pass through, right? The ship didn't pass through, so they place sea mine to block nations from receiving the supply. And then there are counter-offensive or counter-operations that send out my swimmer, right? So that they have this huge magnetic attack, sea mine being placed on the bottom of the sea. So it's all up to the operator to determine how sensitive you want the mental detector to be. Because if you accidentally run into one of this, it could be a matter like a task. Right? So some people will say, hey, to be on the safe side, I want it to be as sensitive as possible. But you might actually run into other critters, right? Because everything that's made of metal or some other object would be classified as a sea mine, right? That means you have good probability of committing type 1 error. False positive. You predict something to be positive, to be 1. Say everything lying down the bottom of the sea or those sea mine because they are made of metal. Right? But that's true. But however, that's false because not everything lying down the bottom is sea mine. And you are doing this because you're trying to mitigate type 2 error on the real fear that you might actually ignore something that's really sea mine, right? But you just did that to be false. It had to be 0. So that's false negative. Hence, the chance of committing these 2 types of error are inversely proportional to each other. So if you reach the sensitivity of mental detector to mitigate the occurrence of type 2 error, then the chance of running into type 1 error, false positive, That's the increase. So we can actually map it into a 2x2 table. So here is a list of the actual cases. You can actually place that differently. But say generally, if you would like to place the application actual cases on the vertical axis and predicted class on the horizontal axis. You see that? The true positive means that both the actual class and the predicted class are all positive and they are all 1. Okay? While the true negative corresponds to a situation in which they all said the outcome to be false or that to be negative. This two guys probably require some effort to understand. So we first go to this one. First, the false positive. That's the type 1 error. That means I predict something to be positive, right? While in actuality, actual pie is negative, so that's why your prediction is false. You predict to be positive, but it's false. So now we get to this one. False negative. That corresponds to type 2 error. That means that the actual case is positive, but you predict that to be negative or 0, right? So that's false. Because the actual case is positive. Make sure you understand this. And in distribution, that means there are some cases that intermingle between this distribution of non-hypothesis and alternative hypothesis, meaning that in this region we want it to be true, and in this region we want it to be false. Some they actually say some of the cases that we need to show actually rely on the true non-hypothesis. Okay. But on the other hand, there are some the actually false event also lie the distribution of true event. So we need to quantify the error we made that we might encounter in classifying this. Type 1 error means false positive. You predict something to be positive, or in actuality it's negative. So the actuality is negative, but you predict that to be positive. Type 2 error, false negative. You predict the outcome to be negative or 0. But in reality, it's positive or 1. So that's here. Predict that to be positive, but in actuality is negative. Alright, so now we have clarified the concept and talk about the related classification matrix quantify such information. So the first one is sensitivity. Or if you read all the textbook, or depending on what field you're in, it has a different name. So some people call it recall or true positive rate. So it describes the test's ability to identify the occurrence of true phenomena among cases that actually have such a phenomenon. So that is tautological. That have this phenomenon definitely are things that have that phenomenon. If you're being tautological, it doesn't make any sense. Well, it does, because once identified, so because we want to maximize the number of predictions that we correctly predict something that's true. Right? Total number of true positive. Because there are cases that are false negative, but in reality, the outcome is true, right? They want to maximize the total number of true positive cases that we predict, but we're also minimize the number of false negative that we have in the prediction that we make. So the higher the score, the more accurate our model. opposite side of it, there is a concept of specificity. Again, it describes the possibility to correctly reject cases that actually did not have a particular phenomenon. And that means we aim to maximize the number of true negatives that we navigate the outcome is 0, and we predict that to be 0. Now, there are also cases in which the outcome is false positive. You predict that to be positive for something percent, but in reality it's negative. It does not percent, right? So that the higher score, the better the variability of your problem. And another concept called precision is the percentage of the correctly predicted true event. So we tend to maximize the number of true positive, but however, the denominator is quite different. Right? It differs from sensitivity by this one is a false positive. So this in this measure, we can maximize the number of correctly predicted cases from the sum of correctly predicted cases and the incorrectly predicted cases. That means false positive. So here I should show you an example. It's actually from a published paper. So if you're interested in that, you can click on this. I already give it a hyperlink. So you say, right, so they don't look logical. So when and where should I use say certain metric to evaluate the precision or evaluate the accuracy of my model? So here, this author actually tries to deal with an event called arms transfer. And say like many international relation phenomena, for example, like war, because countries are mostly at peace. Let's say are at peace most of the time. And also like institutional reform, because there's an old saying, if not broken, then don't fix it, right? So will really reform their institution only when needed, right? So you try so if you study international security, you say, we're trying to model the occurrence of war and try to calculate the prediction accuracy. Then you kind of run into this problem because most of the time the country are at peace, right? So you should expect there's lots of zero in your data, and so even if your model correctly correctly predict most of this, most of the zero outcome negative cases, that probably say little about the predictive power of your model because, well, country are mostly at peace, right? And those zero observation are somehow irrelevant. So here it is not to say, okay, so because the subject that we are studying is a real event. So using sensitivity or recall could be more relevant because we only study the percentage of our correctly predicted event from the subset of the cases that actually have such an event, so that we essentially narrow down the population. So we simply narrow down the number of observations in your denominator. And as said, it could be a more demanding metric, more demanding criteria in the receiver operating characteristic. So that's what they said, and you can take that as a reference. That's just for your reference. There are other methods, the F1. I still use this one. So harmonic mean is inverse of arithmetic mean of the receiver code given standard observation. Another one that I use all the time is on your assignment, accuracy. Measure the chance of correctly predicting true positive, true negative among all cases. So let's go into like when you care about percentage of correctly predicting cases, whether they are true positive and true negative. There is also false positive rate. It's the probability of incorrectly rejecting a true null hypothesis among all negative cases. So you said it's just the complementary probability of specificity here, but specificity here about the ability of the model to correctly predict true negative cases among cases that are all negative. So false positive is just the complementary probability, which is 1 minus specificity. Second example, as the probability of incorrectly rejecting the true null hypothesis among all negative cases. So now, since we have the matrix, now we introduce methods to visualize their performance based on this matrix. So the first one is ROC, or receiver operating characteristic. And area under the curve. So these two concepts are it's a different side of the same coin. They are related. So the first, the ROC is just a graphical method that will diagnose the ability of a binary classifier. It has to be binary classifier. And now the multinomial classifier. Why? We'll say that is, I don't see anyone like that. Because the matrix that we use is built on this 2x2 table. Right? So if you're doing like a three type, it's going to be classified 3 type outcome or 4 type outcome that wouldn't be able to add on to this 2x2 table. And then you can add construct your say construct this matrix to see classify the application outcome on this multinomial classifier. And this I have to see. So essentially plot the diagnostic ability of the model, finite classifier as this discrimination measure change. So the related question, the more relevant question to ask is, so what are those classifiers? What are those discrimination measures? Well, they are true positive rate and false positive rate. So true positive rate is the probability that your model correctly predict the true event at random. Right? You can correctly sort positive cases to positive group, negative cases to negative group. And the false positive rate, that means the model minimizes the probability of incorrectly sorting cases to the wrong group, right? So the false positive rate and the true positive rate and the false positive rate should be inversely proportional to each other, or they share an inverse relationship. So that if you plotted the ROC receiver operating characteristic curve, then you see that it's generated by plotting the cumulative distribution function of detection probability, so the ability of your model on the vertical axis, versus the cumulative distribution function of a false positive rate, plotted by the specificity, on the horizontal or x-axis. So that the curve, if the curve have higher true positive rate, right? So we predict true positive cases most of the time. Then lower false positive rate, reject true null hypothesis most of the time. Then you should have higher area under the curve and therefore set that better diagnostic ability. Here probably baseline is 1.5. Meaning that it's not so different from tossing a coin because you expect to be correct 50% of the time. So you can see that for any given data point at different classification thresholds. So it's like here. We set sensitivity for the true positive rate to 0.4 its specificity to 0, right? Then we move along line, and we increase the sensitivity to 0.6. And then put that up to say 0.05, something like that. So that if you have higher area under the curve, then your model is said to have better diagnostic ability. So for example, if you have another curve lying below this blue curve, that should have lower area under the curve than the blue curve. That means its ability to correctly sorting cases, positive case to positive curves, or cases, negative case to negative, is lower than this one, right? Because it has lower area under the curve. So to adjudicate the predicted performance of the two models, you should favor this blue one relative to other model that's lying below. So that's the evaluation function. So we're playing around with that. So to do that, we need to install lots of package. So SPN, the graph, we use to train test split, and the HFDN data, and PROC, that's the package we use for plotting. Or actually, there are a bunch of different R packages that can do the same. So, but here, just for pedagogical purposes, just use PROC, but if you don't know what to use other packages. Plot RC, and some machine learning R package or Python package, they have their own built-in RC function. So you can also use their function. So we get all the data, and then we simply convert that to numeric class, and we subset in a column, which serve as our variable. We subset data to observation that do not have recent value, and we do trend path split, which we're familiar with. And so we first create a logistic regression model, and then we do prediction. So we run the model on training data and predict on casting data. So the first one should be the regression output that we make. And you should see that the classification performance, as you see, the classification results are very sensitive to the threshold. Right? The threshold is actually assumed bias. So the proportion of type 1 error, type 2 error should change as a function of your discrimination threshold. So that was our use to say on the jargon that you probably heard about recently in the wake of another COVID uprising. Talk about CT value. CT value. They said, oh, should we raise our CT value or lower? CT value means cycle. Just heard on the news this afternoon said that if someone was being asked the city treasurer higher than 30, then they should be allowed to go home. They're probably safe or risk-free, like low risk of having been infected with COVID. Right? The COVID is, say, it's pretty much like it's a matter of life and death, right? So at the initial of this COVID pandemic, and so because we have low infection rates, so the government can actually dedicate lots of effort into containing this pandemic. So they actually said the CT value will be very low, right? So see that initially considered at 5 to 7. So if you got something that is higher, lower. No. When I say very high, so, and it's very common to people who reach under something, and you are immediately sent to the hospital. But for say over time, since this pandemic has pretty much lasted for over 2 years, and most national government have say already squandered lots of resources in containing the disease, so they're pretty much fed up. All right, we can tolerate for more classification error. For instance, say about 1/3, say in most countries, about like 1/5 or even up to 1/3 of the population have already been infected with causes that they just don't treat. So they can actually lower down the CP pressure, the cycle pressure, to embrace more classification error. So you see that. If I set that to 0.1, then here's my diffusion matrix. Okay. However, if I set that to say 0.25, and you see that well, the true positive rate actually decreases. You see the lower right quadrant. We can also calculate using their function, their sensitivity specificity function to calculate that. But in order to do that, we should, and so I have to remind you that you will probably encounter this problem in your forced assignment, because they require lots of conversion. You can convert effective class to numeric class, or convert a string to factor or to numeric, so they haven't do that either. But you should be able to find most of the guide on or up and down. So in order to calculate that, of course, we need our true value, right, and the predicted value. So we need to convert that to the factor class and fit it into the sensitivity function. We'll calculate this for you as specificity function, which is the same. And since we have converted one of our true value, which is denied, this is subset from the testing data, so we create one additional variable on it. So we should subtract that, because we're going to use that for the following classification model. So we kind of convert it back to its original form. Also for the outcome variable, to convert that to numeric. Of course, there are easier ways to do confusion matrix. You just get tired to make those tables. You should just use the rank class and then call its confusion matrix function and fit your model on here, so you would generate that. But it's just not very intuitive, right? So it doesn't look like this confusion matrix that we're going to use. We can also do the same model for probit. As you can see, they're also sensitive to your classification pressure. Then we can also do support mapping machine as a classification model. So as I said, we fit the model on training data and generate an SVM output, and then we create an output, predict this trend model on the testing data, and generate confusion matrix. And again, since after conversion, we need to remove the converted variable. And finally, we can use gradient boost machine that we just learned last week. And here's an interesting function that we use. It's about timer, right? Because last week I said, the gradient boost machine may require more tree to get a better estimate, and you were consuming lots of time. So what do you actually want to find out? So how much does it take, right? So you should be familiar with this. You're a TikToker for a living, right? So just go to the library and TikTok and close the gradient boost machine model inside it. As I simply said, set or the type of parameter here, but you can adjust that to different level. And again, use your trend model, predict testing data to generate predicted outcome. And then, again, you may be subject, be very sensitive to your threshold value. And you can also create a diffusion matrix and calculate accuracy score. So you should probably be familiar about why the accuracy score is calculated this way. Because accuracy is defined as true positive plus true negative, although true positive plus false positive, true negative. So we only retrieve those values on the upper left diagonal and the lower right and divided by the sum of the number of muscles. And since it will show percentage terms, so if you want to read it as percentage, you need to multiply by it. So that you should probably know what's really going on. So now we have pretty much all the material or all the ingredient we need. Now there's one final step before we can actually use this ingredient to make sausage, right? The sausage we can just create that one by one. So in order to calculate the ROC AUC score, that default you need ROC and UC, right? You need R or simply any sort of programming language you are working on to calculate the receiver operating characteristic, which is simply plot the cumulative distribution function of your true positive and false positive rate, right? From all this statistic that we just run. So R can actually very easily and do this for you on the so it's just called the ROC function. And then use that to impose the true value and your predicted value to generate the ROC object for the logit model. So I just name it as ROC logit. And we can also do the same for probit, right? So ROC probit, now we have it at SBN, but you should be mindful that since the SBN's programming machine prediction outcome is cell effective class, so we need to transform the predicted outcome to numeric in order to fit into the ROC function. So that's the kind of error that you may encounter. But I mean, when that happens, just don't worry. Just look at the error message to tell you what to do. So that now lots of conversion, right? And then you use the ROC function to generate ROC SBN. Same for the gradient boost machine. Also do that, right? So the graph isn't very pretty, but it's just like this. So we can plot that into a graph. But use the simplest function. Of course, if you want to have more aesthetic, you can use ggplot too. But here, just use the plot function based on. So I first create a plotting environment using ROC logit. And then I keep adding additional line for other 3 model, ROC probit, and color it blue. ROC SBN all in red, ROC green, color in green. Then I created a legend that way how my reader will better understand what's inside the graph. Okay. So legend is a model, and by different models, lay on top of each other. Okay. Also, I give it a different color. So black is is mapped to ocean, blue is mapped to proven, it's been mapped to red color, and green is machine mapped to green color. The line type, I always set that to just a straight line. Okay. Here I didn't do any additional adjustment. I said, so where is AUC, area under the curve? Should we calculate some sort of area, right, to quantify this information? And we can directly do that using the BUC function. To calculate from the ROC object you just created. So we first create the ROC function using AUC. And then the AUC of the curved ROC object. You see a support map to ROC. You see a green boost machine ROC. And then we get those numbers, we then map onto our legend. We just really use this legend referring to an average to close this additional information. And then we show that in the legend. So this is a good way to present the information and give some how we can read it on this table. The ability of the various classification models that you did. So you can see that the gradient boost machine has the highest area under the curve. So by default, you should have the highest prediction followed by the inclusion model. You see that the ratio. The program probably working a little better than some machines. Okay. All right, so that's pretty much it. Any question? All right, so that's pretty much sum up today's lecture.